All right, let's talk about one of the most famous and probably one of the most misunderstood ideas out there, the butterfly effect. You've heard this, right? Some version of it anyway. It's this beautiful, poetic idea that a tiny, tiny action over here can cause some massive event way over there. It's a huge theme in science fiction.
So is that really it? Is it all about one little butterfly causing one specific tornado? Well, the real story is way more complicated, and honestly, a lot more profound. It's not really about power or control. It's about the very limits of what we can know.
To really get what the science is saying, we kind of have to peel back all the layers that pop culture has built up around this idea. Think about it. In movies and books, the butterfly effect is almost always treated like a superpower, a form of leverage. You know, the hero finds that one little moment in the past, steps on the right bug or saves the right person, and bam, they can control the future. It's this really tempting fantasy, right? That our small choices can have these huge, direct, and predictable consequences. But here's the thing. That idea of using a tiny action like a lever to get exactly what you want in the future, that is precisely what the real butterfly effect is not about. The actual scientific insight is so much deeper, and in a way, it's a lot more humbling. You see, the real story doesn't start with a time machine. It starts with a meteorologist, a really old computer, and a simple rounding error that basically changed how we see the universe. It's one of those amazing stories of accidental discovery. So, back in the 1960s, there's this guy, a meteorologist named Edward Lorenz. He's using one of those early room-sized computers to try and model the weather. He's got these 12 equations for things like temperature and wind speed, and his big goal is to figure out if we can predict the weather way, way out into the future. So one day, he wants to rerun a simulation, but to save a little time, he decides to start it from the middle. He takes the numbers from an earlier printout and just types them back in. But here's the catch. The printout only showed 3 decimal places, 0.506. The computer's memory, though, was holding 6 decimal places, 0.506127. He figured, what's the difference? It's a tiny, tiny rounding error. It shouldn't matter.
Oh, but it mattered. That minuscule difference, less than 1 part in 1,000, it didn't just slightly change the weather prediction. It created a completely different one. Lawrence started the simulation, went to get a cup of coffee, and when he came back, the weather in his computer had gone completely haywire.
For a little while, the two simulations looked pretty similar. But then, as Lorenz himself put it, that tiny error started to grow, doubling in size every few days until the new weather pattern had absolutely zero resemblance to the original. A microscopic difference had snowballed into a totally different world. Lorenz hadn't found a way to predict the weather. He'd accidentally discovered why long-term weather prediction is actually impossible. And that stunning discovery, well, it kickstarted a whole new branch of science, a field built around a really beautiful and mind-bending paradox. This is chaos theory. Now that sounds complicated, but the phrase you really want to lock in on is sensitive dependence on initial conditions. All that really means is that for some systems, the exact starting point matters a lot, like with an almost infinite amount of precision. And this brings us to this amazing paradox. Lorenz's weather simulation was totally deterministic. There was no randomness. If you could put in the exact same numbers down to the very last decimal place, you'd get the exact same weather every single time. But here's the kicker. In the real world, we can never, ever measure anything that precisely. And in a chaotic system, that tiny bit of uncertainty doesn't just make predicting the future hard, it makes it fundamentally impossible. So, here's the real takeaway. The butterfly effect isn't about finding the one magical butterfly that will cause the exact tornado you want. It's the realization that there are millions of butterflies and moths and breezes and tiny changes in temperature, and you have absolutely no way of knowing which one is going to be the one that matters. You can't control it. And this isn't just some abstract idea stuck inside an old computer model. This sensitive dependence thing, it shows up all over the place, in some of the most important and complex systems that run our world. I mean, the most obvious one is the weather, of course. This is why weather forecast gets pretty shaky after about a week. Meteorologists know this. So instead of just running one forecast, they run what are called ensemble forecasts. Dozens of simulations where they tweak the starting conditions just a tiny bit to see the whole range of possible weather we might get. Then you've got economics. The mathematician Benoit Mandelbrot realized that chaos theory could explain financial markets. He said, look, the standard models just can't explain these sudden, wild crashes and booms. He saw the market as a chaotic system where some tiny, unseen event, a political rumor, a single big trade, could set off a massive chain reaction. And really, what is human history if not one gigantic, unbelievably complex, and chaotic system? So many of the biggest events seem to hinge on the smallest of chances. Just think about how World War I started. Archduke Franz Ferdinand's driver takes a wrong turn in Sarajevo, a 1 in a million chance. The car stalls, and it just happens to stop right in front of the assassin. Was that wrong turn the butterfly? Yeah, in a sense. But it was just one of countless tiny, unpredictable moments that day that rippled through the incredibly tense political situation in Europe and led to a global catastrophe. So, when we pull back from the science and the history lessons, what does this all mean for us, for how we look at the world and our own place in it? Well, the implications are actually pretty philosophical. For a long time, the dominant scientific idea was this clockwork universe. The idea that if some super smart being knew the position of every single atom, it could calculate the entire future perfectly. The future was already written. But chaos theory gives us a very different picture. A universe that might follow fixed laws, but whose long-term future is impossible for us to know, all because we can never know the present perfectly enough. And decades before Lorenz, a brilliant mathematician named Henri Poincaré had already glimpsed this. He saw that for some systems, prediction itself just breaks down. He was peering over the edge of a philosophical cliff that Lorenz would later map out for all of us. So what's the deep meaning here? What should we take away from all this? Well, for one, we have to be humble about our ability to predict the future. But more than that, we have to realize that we live in this unbelievably interconnected web, where even our smallest actions could have massive, unknowable consequences. And that's not about being powerless. It's the opposite. It's about responsibility. It's about understanding that our choices matter in ways we might never, ever see. And that leaves us with a really big and really challenging final question. The butterfly effect doesn't give us a roadmap for controlling the future. It tells us that roadmap is impossible to create. So if we live in a world of endless complexity, where every single choice we make could ripple out in ways we can't possibly foresee, how should we choose to act? That's a question worth thinking about.